The universe is bound together by invisible threads. Carl Sagan once said the cosmos is within us, that we are made of star stuff. This is not just poetry. It is a scientific truth pointing to the fundamental forces that literally hold reality together. Your journey through this story will permanently shift how you see your own place in the cosmos. We will travel from the force that keeps your feet on the ground to the very light that lets you see, revealing how these cosmic binders connect the largest galaxy to the smallest atom. How can a single force both anchor you to the Earth and orchestrate the dance of entire galaxies? What does the nature of light itself tell us about the beginning of everything? What one question about the universe have you always wanted answered? That pen hits the floor, a tiny event echoing a cosmic law. Gravity is the great architect of the cosmos, the silent composer of an immense, invisible symphony. It began with a falling apple and a brilliant mind, Isaac Newton, who gave us the mathematics to describe this pull, but it was Albert Einstein who completely reshaped our understanding. He revealed that gravity is not some mysterious force reaching across space. Instead, think of the universe as a vast, stretchy fabric. Planets, stars, and galaxies are like heavy weights placed upon it. Each weight creates a dip, a curve in that cosmic fabric. This curvature is what we experience as gravity. The Earth does not pull on the moon with an invisible string. The Earth makes a deep well in space-time, and the moon simply rolls around the rim of that well, forever caught in its curve. This single idea explains so much. It explains why the planets orbit the sun, not because they are pulled, but because they are following the curved paths the sun creates. It predicts the existence of black holes, objects so massive they create pits in space-time from which not even light can escape. It even governs the grandest scale of all, the expansion of the entire universe. Every high and low tide on our planet is a direct physical conversation with the moon, a demonstration of this invisible, flexible geometry that connects celestial bodies across vast distances. From the apple dropping from a tree to a billion stars swirling around a galactic core, it is all the same phenomenon. This foundational force, this bending of the cosmos itself, sets the stage for everything that follows. That same cosmic fabric, curved by gravity, holds another secret force, one that builds the very substance of reality. If gravity is the grand architect of the cosmos, then electromagnetism is the master builder of the atomic and molecular world. Think about the simple magnet clinging to your refrigerator. That small, persistent pull is a direct glimpse into one of the universe's four fundamental forces. Electromagnetism is the force that governs the chemical bonds forming every single object you will ever touch. It is the reason your screen emits light and your nerves carry signals. It is the very glue that holds atoms themselves together. In the 19th century, a scientist named James Clerk Maxwell wove electricity and magnetism into a single, elegant theory. His equations did more than just unify two ideas. They predicted the existence of something astonishing, waves of pure energy traveling across the emptiness of space. These are electromagnetic waves, and they make up the entire spectrum of light. From the long, gentle radio waves that carry music to your car, to the narrow band of visible light that paints the world for your eyes, all the way to the incredibly powerful gamma rays born in the hearts of exploding stars, it is all the same phenomenon. Without this force, atoms would fly apart. There would be no chemistry, no solid matter, and certainly no life. Its influence is both intimate and immense, crafting the detailed architecture of reality from the ground up. But that powerful electromagnetic force, the very one that builds our molecular world, presents a profound puzzle inside the heart of an atom. Venture into the nucleus where protons are crammed shoulder to shoulder. Each one carries a powerful positive charge, and identical charges violently repel each other. So why does the nucleus not instantly explode? What unseen hand holds these rivals together against their will? The answer is the strongest binding agent in the cosmos, the strong nuclear force. This force is so immensely powerful it completely overwhelms the electromagnetic repulsion, but it operates with an incredibly short leash. Its influence is confined to the tiny, crowded neighborhood of the atomic nucleus. This force works in two incredible stages. First, it acts as the ultimate superglue between the fundamental building blocks known as quarks, binding them tightly to form the protons and neutrons themselves. Then, with strength to spare, it reaches out just a little further to bind those protons and neutrons together into stable atomic nuclei. This is the silent, non-negotiable anchor that makes matter possible. Without this force, every atomic nucleus in the universe would instantly fly apart. There would be no elements, no chemistry, and no solid stuff for planets or people to be made from. It is this same formidable power that enables the fires of stars to burn. Inside the core of our sun, the intense pressure and heat force hydrogen nuclei incredibly close, allowing the strong force to take over and fuse them into helium, a process that unleashes the light and energy that sustains life itself. From the stability of the air you breathe to the warmth of sunlight on your skin, you are experiencing the direct consequence of this ultimate cosmic glue. Yet within the tight confines of the atomic nucleus, where the strong force rules with absolute power, another, more subtle player works in the shadows. This is the weak nuclear force, the universe's ultimate agent of transformation. While its name suggests insignificance, its role is anything but. The weak force is the cosmic alchemist, the only force capable of changing one type of quark into another, and in doing so, it can literally rewrite the identity of an atom. Picture a single neutron, a particle that is perfectly stable when locked inside a nucleus but becomes restless and unstable when alone. It yearns for a different state. The weak force provides the path. It allows that neutron to transform itself into a proton. In this remarkable process known as beta decay, the neutron ejects an electron and an almost undetectable particle called an antineutrino. One particle becomes three entirely different ones, a fundamental identity shift at the heart of matter itself. This obscure-sounding transformation is one of the most vital processes in the cosmos. Inside the furious heart of a star, where the strong force fuses hydrogen into helium, it is the weak force that keeps the stellar engine churning. It enables crucial steps in the chain of nuclear fusion, allowing stars to build progressively heavier elements. Without this subtle force, the fusion process would stall, and stars would be unable to create the carbon, oxygen, and other elements essential for planets and life. The weak force's ghostly signature led to one of physics' greatest predictions. Scientists studying beta decay noticed that energy seemed to go missing in the transformation. To balance the cosmic books, the brilliant physicist Wolfgang Pauli proposed the existence of an invisible, elusive particle carrying that energy away. This was the neutrino, a spectral traveler that can pass through light years of lead without a single interaction. The fact that we can now detect these cosmic ghosts is a testament to the weak force's reality and power. It is the quiet, transformative hand that reshapes the building blocks of reality, fueling the stars and seeding the universe with the diversity of elements that make our very existence possible. Einstein's spacetime is not just a stage, it is a dynamic actor in the cosmic play. Picture a perfectly still, taut rubber sheet. Now place a heavy bowling ball in its center. The sheet stretches downward, forming a smooth, deep depression around the ball. This simple model captures a profound truth that mass warps the very fabric of reality. The Sun, a colossal weight in our cosmic sheet, creates an immense curvature in the spacetime around it. The Earth does not orbit because it is being pulled by some invisible rope. It simply rolls along the curved contour of that depression, like a marble circling the rim of a funnel. This curvature is gravity itself, not a force but a property of geometry. This single, elegant idea explains phenomena that Newton's gravity could not. It predicts that even light traveling in a straight line through this curved spacetime will have its path bent. During a solar eclipse in 1919, astronomers confirmed this very fact, observing starlight curving around the Sun, a direct validation that mass tells spacetime how to curve and spacetime tells mass how to move. This flexible fabric also ripples. Cataclysmic events like the collision of two black holes send vibrations racing through spacetime at the speed of light. These are gravitational waves, faint tremors in the cosmos that we can now detect, listening to the very echoes of spacetime itself ringing like a bell. From the orbit of a planet to the path of a light beam, everything is governed by the contours of this invisible, malleable fabric, the ultimate arena where the universe unfolds. While the weak force reshapes atoms in stellar cores, its work is ultimately announced to the universe by a cosmic herald, light. This radiant energy is the universe's ultimate messenger, carrying stories from the deepest past directly to our eyes. Every time you look up at the night sky, you are engaging in a form of time travel. The light from the star Proxima Centauri takes over 4 years to reach us, so you see it not as it is tonight, but as it was over 4 years ago. Gaze upon the Andromeda Galaxy, and your vision stretches back 2.5 million years. The most distant galaxies we can detect appear to us as they were billions of years in the past, mere infants in cosmic terms. This is possible because light travels at the universe's ultimate speed limit, an astonishing 300,000 kilometers per second. Nothing with mass can ever reach this speed, let alone exceed it. This constant, universal speed limit is not just a traffic law for the cosmos. It is a fundamental property of reality itself, woven into the fabric of spacetime. But what is light, this entity that defines the very rules of existence? It presents us with a profound and beautiful paradox. In some experiments, light behaves exactly like a wave, rippling through space with characteristic wavelengths that define its color. In others, it acts as a stream of tiny, discrete packets of energy called photons. This is not a contradiction, but a fundamental truth known as wave-particle duality. A single photon is both a particle and a wave at the same time, its true nature revealed only by how we choose to observe it. This bizarre behavior is the cornerstone of quantum mechanics, and it governs how energy is transferred across the universe. The warmth you feel on your skin from sunlight is the collective impact of countless photons, each a tiny particle of energy delivered from 93 million miles away. The information streaming through a fiber optic cable carrying the entire internet is encoded in pulses of light, from the grandest cosmic vistas to the most intimate technologies of our daily lives. Light is the indispensable bridge, the constant stream of information that binds our local experience to the vast, distant, and ancient cosmos. This bizarre wave-particle duality is just the beginning of the quantum story. To truly grasp how the cosmos is bound at its most fundamental level, we must venture into the quantum realm, where our everyday logic completely breaks down. This is a world of ghosts and probabilities, a domain governed by rules that seem to defy common sense. Here, a single particle, like an electron, does not have a definite location. It exists as a cloud of possible positions, a haze of potentialities spread across space. This is the principle of superposition, where an object can literally be in multiple states or places at the same time. It is only when we attempt to measure it, to pin it down with our observation, that this cloud of possibilities collapses into a single, definite reality. This inherent uncertainty is not a flaw in our measurements. It is a fundamental property of the universe, baked into the fabric of reality at the smallest scales. This probabilistic nature is the very glue that holds atoms together. If electrons behaved like tiny planets with fixed orbits, they would spiral into the nucleus and everything would collapse. Instead, their fuzzy, probabilistic existence creates stable shells that allow atoms to form and molecules to link, giving rise to the entire world of chemistry and ultimately to us. But the strangeness deepens with what Einstein called spooky action at a distance, known today as quantum entanglement. This phenomenon creates a mysterious connection between two particles, linking their fates no matter how far apart they travel. Change the property of one entangled particle, and its partner instantly reflects that change, seemingly communicating faster than the speed of light. This is not science fiction. It is a tested and confirmed feature of our universe, suggesting a level of interconnectedness that challenges our deepest notions of space and separation. This quantum underworld is not some distant curiosity. It is the active foundation of our reality. It governs the nuclear fusion powering our sun, dictates the laws that build complex molecules, and underpins the technology of modern computers. The predictable, solid world we experience is built upon a hidden quantum landscape of shimmering potential and ghostly connections, a reminder that the most fundamental bindings of the cosmos are woven from threads of probability and mystery. The ghostly connections of quantum entanglement hint at a hidden layer of reality, but there is an even larger and more pervasive mystery woven into the fabric of the cosmos itself. Our universe is held together by a substance we cannot see. When astronomers measure the speed at which stars orbit the center of their galaxies, they find something deeply puzzling. According to the laws of gravity, the stars on the outer edges of a spinning galaxy should be moving much more slowly than those near the center, just as the outer planets in our solar system have longer, slower orbits. Yet the data reveals the opposite. These distant stars are hurtling around at incredibly high speeds, so fast that the gravity from all the visible stars, gas, and dust in the galaxy is utterly insufficient to hold them in place. The galaxies should be tearing themselves apart. Something else, something invisible, must be providing the extra gravitational glue. We call this missing ingredient dark matter. Its presence is felt only through its immense gravitational pull, a ghostly hand gripping the cosmos. We see its signature again in a phenomenon called gravitational lensing. Einstein's theory tells us that massive objects curve spacetime, bending the path of light. Sometimes we observe light from a distant galaxy warping and bending as it travels to us, but there is no visible source of mass large enough to cause the distortion. It is as if space is filled with invisible lenses, the gravitational footprints of dark matter weaving a scaffold that holds entire clusters of galaxies together. Without this unseen framework, the majestic structures we observe in the night sky would simply not exist. So what is it made of? It cannot be ordinary matter like planets or dead stars, as it does not interact with light at all. It does not emit, absorb, or reflect any form of electromagnetic radiation, rendering it completely transparent to our most powerful telescopes. the leading candidates are exotic particles that barely interact with the normal world. One possibility is weakly interacting massive particles, or WIMP, heavy theoretical particles that pass through our planet like ghosts through a wall. Another candidate is the action, an ultra-lightweight particle that might be flooding the universe. Whatever its true nature, dark matter is the silent, dominant architect of the universe's large-scale structure, a cosmic reminder that most of the gravitational force shaping our reality comes from a realm we have yet to see. This mysterious dark matter, however, is only half of the story. While its immense gravitational pull works tirelessly to sculpt and hold the cosmos together, a far more bizarre and dominant force is working in the opposite direction. In the late 1990s, two independent teams of astronomers were observing distant stellar explosions to measure how fast the universe was expanding. They fully expected to find that the mutual gravitational pull of all the matter in the cosmos was putting a brake on this expansion, gradually slowing it down over billions of years. Instead, their data revealed something utterly shocking. The expansion of the universe is not slowing down at all. It is accelerating. Galaxies are flying away from each other at a faster and faster rate, as if some unknown repulsive force is stretching the very fabric of spacetime itself. This mysterious cause was dubbed dark energy. Think of it as a kind of anti-gravity, a pervasive pressure inherent to empty space that acts on the largest imaginable scales to push the cosmos apart. Its nature is arguably the greatest puzzle in modern physics, even more elusive than dark matter. One leading idea is that dark energy is a fundamental property of space itself, an energy of the vacuum. Empty space is not truly empty, according to quantum physics, but is a seething foam of virtual particles popping in and out of existence. This activity could be generating a constant repulsive force that Einstein once called the cosmological constant. Another possibility is that dark energy is a dynamic field that fills the universe, a cosmic fluid whose properties change over time. Whatever its true identity, its dominance is staggering. Combined, dark matter and dark energy make up about 95% of the total content of the universe. Everything we can see and touch, all the stars, planets, and galaxies, constitute a mere 5% of reality. The discovery of dark energy completely overturned our long-held vision of the cosmos. It erased the idea of a universe destined to one day recollapse in a big crunch, or even to coast gently to a stop. Instead, it paints a picture of a cosmos driven by an unseen accelerator, racing toward a future where galaxies will be pushed so far apart that their light will never reach one another again. This invisible force is not just shaping the universe, it is commanding its ultimate fate. This cosmic acceleration driven by dark energy presents a stark contrast to another invisible field, one that gives substance to the universe rather than pulling it apart. For decades, physicists were haunted by a fundamental question: why do the building blocks of matter have any mass at all? Why are not all particles like photons, zipping through the cosmos at the ultimate speed limit? The answer arrived in a monumental discovery in 2012 with the confirmation of the Higgs boson, a ripple in an invisible ocean known as the Higgs field. Think of the entire universe as filled with this field, a kind of cosmic molasses that is utterly undetectable until something moves through it. Fundamental particles are not inherently heavy. They acquire their mass through their interaction with this all-pervasive field. Particles that do not interact with it at all, like the photon of light, remain massless and travel at light speed. But particles that do interact, like the electrons and quarks that make up your body, experience a kind of drag. This resistance to their motion through the Higgs field is what we perceive and measure as mass. This mechanism is not just a minor detail, it is the very reason stable matter can exist at all. Without the mass bestowed by the Higgs field, every fundamental particle would race away at the speed of light. Electrons could not be captured into orbits around atomic nuclei. There would be no atoms, no chemistry, no stars, and no us. The Higgs field is not a force like gravity or electromagnetism that pushes or pulls. It is a fundamental property of empty space itself, a cosmic treacle that gives substance to the universe, allowing the ethereal quantum world to coalesce into the solid, tangible reality we experience every day. Yet this cosmic molasses that grants mass is not the final arbiter of our reality's destiny. There is an even more profound and inescapable rule that governs the flow of the cosmos itself, a law that gives time its direction. The universe has a distinct and irreversible arrow, forever pointing from order to disorder. This fundamental principle is the second law of thermodynamics, and it is quantified by a concept called entropy. Think of entropy as a measure of chaos or randomness in a system. The law states that the total entropy of the universe, or any isolated system, always increases over time. It never decreases. Picture an ice cube dropped into a warm drink. The ice begins in a highly ordered, crystalline state, its water molecules locked in a neat, structured lattice. This is a low entropy condition. As it melts, those molecules break free, spreading out and mingling randomly with the liquid. The system becomes more disordered, its energy more evenly distributed. It has moved to a high entropy state, and it will never spontaneously reassemble itself back into that pristine ice cube. This relentless march toward disorder is what gives us the arrow of time. It is the reason we remember yesterday but not tomorrow, why a shattered glass does not leap back onto the table fully formed. Our very perception of time's flow is tied to this irreversible increase in entropy. On the grandest scale, this law dictates the entire story of the cosmos. The early universe, in the first moments after the Big Bang, was in a state of incredibly low entropy. It was an unimaginably hot and dense soup, but a remarkably uniform and ordered one. As the universe expanded and cooled, entropy began its inevitable climb. This increase is not merely a slide into chaos. It is the very engine that drove the formation of structure. The subtle gravitational imperfections in that early soup were seeds of higher entropy, as collapsing gas clouds formed stars and galaxies, converting concentrated energy into heat and light, spreading energy out in the process. But this creative power comes with an ultimate cost. The universe is on a one-way journey toward a final state known as heat death. In this distant future, entropy will reach its maximum. All energy will be uniformly distributed throughout an ever-expanding space. Stars will have burned out, black holes will have evaporated, and no more work will be possible. The cosmos will become a cold, dark, and featureless sea, its story complete. Entropy is the silent, temporal binder that dictates the flow and evolution of everything, from the melting of a single ice cube to the ultimate fate of the entire cosmos. This relentless slide toward cosmic disorder began with a starting point of astonishingly low entropy, a state of near-perfect uniformity that itself presents a profound puzzle. The universe we observe is remarkably smooth and flat on the largest scales. The cosmic microwave background, the ancient afterglow of the Big Bang, shows a nearly identical temperature in every direction we look. How could regions of space now billions of light years apart, regions that could never have exchanged heat or information, have achieved such a perfect equilibrium? The classical Big Bang theory offered no satisfying answer. The solution emerged with a breathtaking concept, cosmic inflation. This theory proposes that a mere fraction of a second after the moment of creation, the universe underwent a violent, exponential growth spurt. In an almost unimaginably brief flash, far less than the blink of an eye, the fabric of space-time itself expanded faster than the speed of light, inflating from a size trillions of times smaller than a single proton to something macroscopic. This was not an explosion in space, but a runaway stretching of space itself. This incredible acceleration acted like a cosmic iron, stretching and smoothing any primordial wrinkles to create the vast, flat, and uniform universe we detect today. Yet, within this frantic smoothing process, something crucial was preserved and magnified. The quantum realm is never perfectly still. It is a seething sea of tiny, spontaneous fluctuations, where particles and energy flicker in and out of existence. During inflation, these minuscule quantum jitters were stretched to astronomical sizes, frozen into the fabric of the expanding cosmos as faint ripples in density. These ripples became the gravitational seeds for everything that followed. Picture a balloon with an incredibly intricate, microscopic pattern drawn on its surface. As you inflate the balloon to an immense size, the pattern is stretched and magnified, becoming the large-scale structure you now see etched across its surface. In the exact same way, those infinitesimal quantum fluctuations, magnified by inflation, became the blueprints for the cosmic web of galaxies and voids we observe today. This brief but monumental event did more than just solve a temperature puzzle. It set the entire subsequent history of the universe in motion. Every galaxy cluster, every swirling nebula, and every star like our own sun exists because of the subtle gravitational fingerprints left by quantum noise, amplified in that first, explosive moment of cosmic inflation. That faint, nearly uniform glow from the cosmic inflation era did not last forever. For about 380,000 years after the Big Bang, the universe was a seething, opaque fog, a plasma so dense and hot that light particles, photons, were constantly trapped, bouncing off a chaotic soup of free electrons and protons. Light could not travel in a straight line, meaning if you had been there, you would have seen nothing but a blinding, impenetrable wall of white-hot glare. Then a pivotal moment arrived as the expanding cosmos continued to cool. The temperature dropped just enough for a fundamental shift to occur. Electrons were finally captured by protons, combining to form the first stable, neutral atoms, primarily hydrogen. In that instant, the fog lifted. The universe suddenly became transparent. Those previously trapped photons were set free, streaming across space unimpeded for the very first time. This first flash of liberated light is the origin of the cosmic microwave background. It is the oldest fossil in the cosmos, a direct snapshot of the universe at that precise moment of its childhood. That primordial light has been traveling ever since, but the expansion of the universe itself has stretched its waves. Over billions of years, the energetic light of a hot young cosmos has been redshifted, its wavelength drawn out into the much cooler microwave part of the spectrum. Today, this afterglow of creation is incredibly cold, just about 2.7 degrees above absolute zero. It fills every cubic centimeter of the space around you, a whisper of heat from the beginning of time. If you turn on an old analog television to the static between channels, about 1% of that snowy hiss is the cosmic microwave background, the literal echo of the universe's birth cry arriving at your antenna. But this fossil is not perfectly smooth. Embedded within its nearly uniform glow are the tiniest of imperfections, minute variations in temperature, mere millionths of a degree. These are the cosmic seeds, the slightly denser and slightly less dense regions that correspond directly to the gravitational fingerprints left by inflation's magnified quantum fluctuations. These tiny ripples in density were the nurseries for everything to come, the gravitational anchors where dark matter began to pool, eventually pulling in normal matter to form the first galaxies, stars, and ultimately us. By mapping these subtle patterns with extraordinary precision, satellites have allowed cosmologists to read the cosmic microwave background like a historical document. It tells us the universe is 13.8 billion years old, reveals its precise composition of dark matter, dark energy, and ordinary matter, and confirms its overall geometry is flat. This ancient light is our most direct and powerful window into the cosmos's first moments, a timeless photograph from the dawn of reality itself. These spectral travelers from the hearts of stars are the universe's ultimate ghosts. Neutrinos are born in the nuclear fires of our sun and in the cataclysmic blasts of supernova, a constant, silent rain from the sky. They are so abundant that they outnumber all the atoms in the cosmos by a factor of billions, and yet you will never feel a thing. Right now, as you listen to this, trillions of them are streaming through your body every single second, passing through the empty space inside your atoms as if you were not even there. This is why they are called ghost particles. They ignore almost everything. They do not interact with the electromagnetic force, so light cannot touch them. They completely bypass the powerful, strong nuclear force that holds atomic nuclei together. Their only cosmic handshakes are through the most subtle forces, the weak nuclear force and the faintest tug of gravity. This profound elusiveness is what makes them so difficult to catch. The very first hint of their existence came not from a direct sighting, but from a crime scene of missing energy. When physicists studied the beta decay of a neutron, the energy books did not balance. Something was carrying away a tiny portion of the energy, an invisible thief. To solve this, Wolfgang Pauli proposed the neutrino, a particle so ghostly he reportedly apologized for suggesting something that could never be detected. Yet we did learn to catch them, building immense, hypersensitive detectors deep underground, shielded from all other cosmic interference. We wait for that one in a trillion event where a neutrino, by sheer chance, interacts with an atom and creates a tiny, detectable flash of light. But why go to such incredible lengths? The answer is that these ghosts are perfect cosmic messengers. Because they pass through almost everything, they carry pure, unaltered information directly from the places we can never otherwise see. A neutrino from the sun's core arrives at Earth just 8 minutes after its creation, giving us a direct look at the nuclear furnace that powers our world. The blast of neutrinos from a supernova arrives hours before the visible light, offering a precious early warning of a star's death. They are a pristine signal from the universe's most violent and creative events, the very processes that forge the heavy elements like gold and uranium. Their influence may even extend to the largest scales of all. We now know that neutrinos have a tiny, almost negligible mass, but it is not zero. In the early universe, untold trillions of these particles, moving at nearly the speed of light, would have exerted a subtle gravitational influence on the distribution of matter. This ghostly pressure could have helped sculpt the cosmic web of galaxies, shaping the universe in ways we are only beginning to understand. They are silent witnesses to the most powerful events in creation, and their faint, persistent whisper holds secrets about everything from the death of stars to the birth of cosmic structure itself. Gravity's final victory is a silent one, a collapse so complete it carves a hole in the universe itself. When a truly massive star exhausts its nuclear fuel, the outward pressure that sustained it for millions of years vanishes in an instant. With nothing left to fight the star's own immense gravity, its core implodes. For stars above a certain mass, this collapse does not stop. It continues until all that mass is crushed into a point of infinite density, a singularity. This is the heart of a black hole, a place where the fabric of space-time, as described by our current laws of physics, simply ceases to exist. Surrounding this unfathomable point is the event horizon, the boundary of no return. It is not a physical surface you could touch, but a one-way membrane in space-time. Cross this invisible threshold, and the gravitational pull becomes so overwhelming that escape would require moving faster than light itself, the universe's ultimate speed limit. From that moment, every possible path leads inward toward the singularity. Nothing, not a single photon, not the fastest rocket, not even information itself, can ever come back out. This makes black holes the ultimate cosmic prisons. They are not voracious vacuum cleaners randomly sucking in everything around them, as often portrayed. Their gravity behaves just like that of any other object. If our sun were suddenly replaced by a black hole of the same mass, the Earth would continue to orbit in complete darkness, held perfectly in place by the same gravitational grip. The profound danger only begins at the event horizon. The warping of space-time around a black hole is so extreme it creates bizarre effects. Imagine you could watch a brave astronaut falling toward one. As they approach the event horizon, you would see their signals stretch out, their clock slow to a crawl, and their image redshift until they seemingly freeze at the threshold, fading from view over an eternity. For the astronaut, however, crossing the horizon might be uneventful, but the tidal forces would soon pull them into a long, thin strand of atoms in a process whimsically called spaghettification. We cannot see black holes directly, but we can witness their dramatic influence on their surroundings. We see stars whipping around an invisible, massive companion at the center of our own Milky Way. We observe disks of superheated gas and dust called accretion disks, swirling at near light speed around the darkness, glowing fiercely with X-rays as friction heats them to millions of degrees before they vanish past the point of no return. The most direct evidence arrived just a few years ago when the Event Horizon Telescope collaboration unveiled the first ever image of a black hole's shadow, a dark silhouette surrounded by a fiery ring of light, the photon sphere where light itself is forced into orbit. Even more astonishing, we can now hear them. The collisions of black holes, events of unimaginable violence, send ripples through space-time called gravitational waves. Our detectors on Earth have felt these tremors, the literal sound of space-time ringing as two black holes spiral together and merge into one. The largest black holes defy comprehension. Lurking at the centers of most galaxies, including our own, are supermassive black holes, weighing millions or even billions of times more than our Sun. Their growth appears to be a fundamental part of a galaxy's life story. When these monsters actively feed, they can become quasars, the brightest objects in the universe, outshining entire galaxies. The energy they release can regulate star formation, heat surrounding gas, and ultimately shape the evolution of the galaxy they call home. A black hole is not just an end, but a dominant force in the cosmic cycle, a gravitational anchor whose silent presence governs the destiny of stars and the structure of the cosmos itself. That silent ringing of space-time is a direct message from the abyss. A century after Einstein's theory predicted their existence, scientists finally captured the first direct evidence of gravitational waves in 2015. The source was an event of almost unimaginable violence, the final death spiral of two black holes over 1 billion light-years away. As they circled each other hundreds of times per second, they churned the fabric of reality itself, sending out ripples that traveled across the cosmos at the speed of light. These are not ripples in water or air, but literal distortions in the dimensions of space and time. When one of these waves passes through you, it subtly stretches your body in one direction while simultaneously squeezing it in another, a distortion on a scale far smaller than an atomic nucleus. How could we possibly detect something so infinitesimal? The answer is an instrument of breathtaking precision called LIGO, the Laser Interferometer Gravitational Wave Observatory. It works by splitting a laser beam and sending the two halves down 4-kilometer-long vacuum tubes arranged in an L shape. The beams bounce off mirrors and return to recombine. In normal conditions, the light waves are tuned to cancel each other out. But when a gravitational wave passes through, it minutely changes the length of one arm relative to the other, shifting the laser light just enough to create a flicker of signal. This is not a metaphor. The first detection was that flicker, a tiny chirp that lasted less than half a second, a whisper that had traveled for over 1 billion years to tell us of a cosmic collision. This single sound marked the dawn of an entirely new sense for humanity. For all of history, we have studied the universe by observing light, from visible rays to radio waves and X-rays. Now we can listen to it. Gravitational waves carry a completely different kind of information. They tell us not how things look, but how they move and shake in the most extreme gravitational fields. Each chirp and ring down reveals the masses of the colliding objects, their spins, and even their distance. This new sense of hearing allows us to probe the dark universe, to study black holes that emit no light at all. It has already confirmed that the black holes we detect this way obey the rules of general relativity, even in realms of gravity so intense they were previously just theoretical. The true power of this new sense emerged in 2017, when a different kind of event was detected. This time, the gravitational wave signal was accompanied by a brilliant flash of light observed by telescopes across the globe. The source was the collision of two neutron stars, the dense, city-sized corpses of dead suns. This event, known as multi-messenger astronomy, was like watching a silent movie and suddenly getting the soundtrack. The gravitational waves told us about the violent merger itself, while the ensuing electromagnetic explosion revealed the creation of heavy elements like gold and platinum, forged in the cosmic fire and scattered into space. We are no longer just stargazers. We have become eavesdroppers on the universe's most profound conversations, listening to the echoes of chaos that reveal an active, dynamic, and often violent cosmos. These immutable rules have been in place since the very first moment. Every force and particle we have explored is governed by a set of fundamental numbers, the universe's fixed settings. The speed of light is not merely fast, it is exactly 299,792,458 meters per second, a constant that underpins the very structure of reality. The strength of gravity, the intensity of the electromagnetic force, the power of the nuclear interactions, all are defined by specific, unchanging values. What is truly staggering is not their existence but their precise values. The cosmos appears to be exquisitely fine-tuned. Alter just one of these numbers by the tiniest fraction, and the entire cosmic story unravels. If the force of gravity were even minutely stronger, the universe would have collapsed back on itself in a fiery crunch long before stars could form. If it were slightly weaker, matter would never have clumped together, and the cosmos would be a permanent, thin haze of hydrogen and helium. The strong nuclear force presents an even more razor-thin margin for error. If it were just a few percent stronger, the nuclear glue would be too powerful. In the early universe, all hydrogen would have fused into helium almost instantly. There would be no long-lived stars, no water, and no cosmic fuel for life. If the strong force were slightly weaker, it could not overcome the electromagnetic repulsion between protons. No stable atomic nuclei would ever form. There would be no carbon, no oxygen, no elements besides hydrogen. the universe would be a barren wasteland of simple, useless atoms. This incredible precision extends to the very expansion rate of the cosmos. The initial push of the Big Bang had to be balanced with breathtaking accuracy against the pull of gravity. Too much force and the universe would have expanded too rapidly for galaxies to coalesce. Too little and it would have collapsed almost immediately. This apparent fine-tuning is so precise it seems to defy random chance. It forces us to confront a profound question. Is our universe a statistical fluke, a one-in-a-trillion lottery ticket that just happened to have the right numbers for complexity and life? Or does this point to a deeper structure, perhaps a multiverse, a vast cosmic landscape where countless other universes bubble into existence, each with its own random set of physical laws and constants? In most of those universes, the numbers do not add up and reality remains stillborn or barren. We find ourselves in the one where the constants align, making our specific cosmic binding not just possible but inevitable. These numbers are the silent, non-negotiable code upon which every galaxy, every star, and every living thing is built. This hidden code of physical constants finds its most elegant expression in a cosmic principle of order, symmetry. Beneath the swirling chaos of galaxies and the unpredictable dance of quantum particles lies a deep and beautiful structure, a set of rules that ensure the universe remains consistent and reliable. This order is revealed through symmetries and the powerful conservation laws they produce. Think of a symmetry as a transformation you can perform on a system where its fundamental behavior remains unchanged. Rotate a perfect featureless sphere and it looks identical from every angle. That rotational symmetry is not just a geometric curiosity, it has a profound physical consequence, the conservation of angular momentum. This is why an ice skater pulls their arms in to spin faster. Their total rotational momentum must be conserved. The universe is built on such principles. Consider the fact that the laws of physics are the same everywhere. An experiment conducted here on Earth yields the same result in a distant galaxy. This symmetry of location, called translational symmetry, leads directly to the conservation of momentum. An object in motion stays in motion unless acted upon by a force, because the universe itself provides no preferred location to slow down. Similarly, the symmetry between positive and negative electric charge ensures that the total amount of electric charge in any isolated system can never change. You can move charge around, but you cannot create or destroy the net amount. This is why when an electron is created, a positron, its positively charged counterpart, must also appear. These laws are the universe's ultimate accountants, ensuring that energy, momentum, and charge are always perfectly balanced in every single interaction, from two billiard balls colliding to the fusion of atoms inside a star. Yet this perfect order is not rigid. When symmetries are broken, new phenomena emerge and reality gains its rich texture. The most profound example is the breaking of the electroweak symmetry. In the searing heat of the very early universe, the electromagnetic force and the weak nuclear force were unified into a single, symmetric force. As the cosmos cooled, this symmetry broke, and in that cosmic transition, the Higgs field switched on, giving mass to fundamental particles. The breaking of that perfect symmetry is what allowed for the existence of atoms, of chemistry, and of us. These principles are the invisible scaffolding of reality, the silent, mathematical music that orchestrates the cosmos, providing a predictable and stable stage upon which the entire drama of existence can unfold. The silent music of symmetry plays out in a cosmic nursery of incredible dynamism. Far from being a perfect vacuum, the space between stars is a vibrant sea of raw material. a place where the future of galaxies is forged. This is the interstellar medium, a diffuse mixture of gas and dust so tenuous that a volume the size of a typical classroom would contain only about a single atom. Yet, across the vast distances of a galaxy, this wispy substance adds up to an immense reservoir of potential. It is within the darkest, coldest pockets of this medium that the magic begins. Here, gravity finds its foothold. Enormous structures called giant molecular clouds containing more mass than 1,000,000 suns drift like cosmic icebergs. Shielded from disruptive starlight by their own internal dust, these clouds grow cold enough for atoms to pair up into molecules, primarily hydrogen. It is within these frigid, dark cradles that gravity can finally overcome the cloud's internal pressure and the faint resistance of magnetic fields. A small knot of gas begins to contract, pulling in more and more material, growing hotter and denser at its core until nuclear fusion ignites and a star is born. The dust floating throughout this medium is far from a simple nuisance. These microscopic grains, composed of carbon and silicates, act as tiny shields. For a nascent star forming deep inside a cloud, this dust is a protective cocoon, absorbing the harsh ultraviolet radiation from nearby stars that would otherwise tear the cloud apart and prevent its collapse. On the surface of these very dust grains, chemistry finds a foothold. Simple atoms and molecules stick to the cold, solid surfaces, meeting and linking to form more complex compounds, including water and organic molecules, the very precursors to the chemistry of life. This cosmic nursery is not a pristine, unchanging place. It is constantly being recycled and enriched. When massive stars die in spectacular supernova explosions, or when gentler stellar winds blow from aging giants, they blast their chemically enriched contents back into the interstellar medium. These stellar ejecta seed the clouds with heavier elements forged in stellar cores, elements like oxygen, carbon, iron, and silicon. The next generation of stars that forms from this enriched material will already be endowed with the building blocks for rocky planets. Our own solar system was born from such a cloud that had been fertilized by the deaths of long-vanished stars. Every atom of iron in your blood and every atom of calcium in your bones was once part of this great cycle, floating in the darkness between the stars before being gathered into the cloud that became our sun and its planets. The interstellar medium is the galactic ecosystem, the stage upon which the continuous drama of stellar life and death plays out, weaving the simple hydrogen of the Big Bang into the complex tapestry of a living universe. These invisible lines of force are the silent conductors of the cosmic orchestra. Magnetic fields weave through the void, an unseen architecture that gives form and direction to the chaos of creation. They are not merely present, they are active, dynamic players. Around our own planet, the Earth's magnetic field acts as a vast protective shield, deflecting the relentless stream of charged particles from the sun and funneling them harmlessly toward the poles to create the shimmering auroras. This same principle scales up to a staggering degree. Our sun is a roiling sphere of plasma, and its internal motions generate a powerful, complex magnetic field. This field is the engine of the sun's 11-year cycle, tangling and twisting until it erupts through the surface as dark sunspots and violent solar flares that can hurl billion-ton clouds of plasma across the solar system. These eruptions are a stark reminder that magnetic forces can accelerate matter to incredible velocities. This is the origin of cosmic rays, subatomic particles racing through the galaxy at nearly the speed of light, propelled by the immense magnetic shocks of exploding stars. On the grandest scales, magnetic fields are woven into the very fabric of galaxies. They stream along the spiral arms, acting like invisible rails that guide and structure the flows of gas within the interstellar medium. This magnetic guidance is crucial for star formation. While gravity pulls a cloud of gas together, the cloud's own internal magnetic field can provide support, resisting the collapse. It is only when gravity becomes strong enough to overwhelm this magnetic resistance, or when turbulent motions tangles the field lines, that a cloud can fragment and collapse into the dense cores that ignite new stars. How is this cosmic magnetism generated? The answer lies in motion. Within stars and in the hot gas between them, electrically conductive plasma is constantly on the move. This churning, swirling motion, driven by rotation and heat, acts as a natural dynamo, continuously regenerating and amplifying magnetic fields from tiny seeds. This dynamo action turns entire planets, stars, and galaxies into powerful electromagnets. So while gravity provides the raw pull to build the cosmos, magnetism provides the intricate blueprint, channeling flows, accelerating particles, and adding a crucial layer of order to the gravitational chaos, directing the construction of reality itself. This overwhelming dominance of matter is the final, fundamental reason you are here to ponder it. One of the deepest puzzles in all of physics is not just how the universe began, but why it is made of anything at all. Our most trusted theories present a stark and troubling picture of the Big Bang. In that initial blaze of energy, the cosmos should have forged perfect, identical twins, matter and antimatter, in absolutely equal amounts. For every proton created, an antiproton should have emerged. For every electron, a positron. These are perfect opposites, and when they meet, they annihilate each other in a flash of pure radiation, leaving nothing behind. If the recipe had been perfectly balanced, every single particle of matter would have found its antimatter counterpart. The entire universe would have cancelled itself out, becoming a vast, eternal sea of featureless light, devoid of atoms, stars, or planets. There would be no stuff. The fact that you are here, that our galaxy exists, is undeniable proof that the scales were tipped. Somehow, for every 1 billion matter-antimatter pairs that mutually destroyed one another in the universe's first instant, a single, solitary matter particle was left behind. Just 1 in a billion survived the annihilation. This tiny, almost negligible excess is known as the Baryon asymmetry, and it is the entire reason the material universe exists. Every single atom in your body, every star in the sky, is built from that 1 in a billion relic. Physicists call the process that created this imbalance baryogenesis, and it requires the universe to have broken some of its own most sacred rules. It needed a fundamental violation of symmetry, allowing processes to favor matter over antimatter ever so slightly. It required conditions that fell out of thermal equilibrium, a cosmic stumble that prevented the system from smoothly rebalancing itself. And it may have involved processes that did not conserve the total number of particles, another deep departure from what we see in our labs today. This is not a minor detail, it is the cornerstone of our material reality. Solving the mystery of Baryon asymmetry is the quest to answer the most profound question of all. Why is there something, in the form of galaxies and life, rather than a perfect and eternal nothingness of light? This overwhelming imbalance in the cosmic recipe points to another, more fundamental rift in our understanding of reality. The universe appears to be built upon a deeply unsettling contradiction in strength. Think about the simple magnet on your refrigerator, effortlessly holding its place against the entire gravitational pull of the planet Earth. That small, everyday victory hints at a staggering cosmic secret. The force of gravity is not just a little weaker than the electromagnetic force that powers the magnet, it is almost unimaginably feeble. In fact, gravity is about 10 to the power of 36 times weaker. That is a 1 followed by 36 zeros. To grasp that scale, if the strength of electromagnetism were represented by the entire mass of our planet, the relative strength of gravity would be the mass of a single, tiny bacterium. This bizarre and enormous gap is known to physicists as the hierarchy problem, and it represents one of the most glaring clues that our current picture of the cosmos is fundamentally incomplete. How can the very force that orchestrates galaxies and holds the universe together be so incredibly weak compared to the forces that build atoms? Our two most successful theories, general relativity for gravity and the quantum model for the other forces, offer no explanation for this ridiculous difference in power. They simply accept it as a bizarre, unexplained input. This is not a minor detail, it is a screaming anomaly that suggests we are missing a crucial piece of the puzzle. One compelling idea to solve this is supersymmetry. This theory proposes a beautiful, hidden symmetry in nature, where every known particle, from electrons to quarks, has a hidden, super-heavy partner particle. In this symmetric world, the quantum corrections that affect the strength of forces would perfectly cancel out, elegantly explaining gravity's apparent weakness. The catch is that we have not found any of these superpartners, despite searching with our most powerful particle colliders. Another mind-bending possibility is that gravity is not weak at all, it just appears that way to us. What if our universe has more than the 3 spatial dimensions we experience? The force of gravity, unlike the other forces, could be leaking out or diluting itself into these hidden, curled-up dimensions. In its full, multidimensional glory, gravity might be as strong as any other force, but we only feel a faint shadow of its true power, a weak echo leaking into our 3-dimensional world. Resolving the hierarchy problem is not just an academic exercise, it is a direct path toward a deeper truth. It forces us to confront the limitations of our current models and compels us to search for a more fundamental theory, one that can truly unify all the cosmic forces into a single, coherent framework. The answer to why gravity is so weak might just reveal the final, hidden elements that bind reality together at its most fundamental level. Even the deepest vacuum of space is not truly empty. It hums with a hidden, seething energy. Quantum field theory reveals that what we call nothing is actually a vibrant sea of activity, a foam of virtual particles that wink into and out of existence in a fleeting dance governed by the uncertainty principle. These are quantum fluctuations, momentary borrowings of energy from the vacuum itself, creating particle-antiparticle pairs that annihilate each other almost instantly. This relentless, underlying activity means that empty space possesses a fundamental energy density, a baseline hum known as vacuum energy or zero-point energy. This is not a speculative idea, it is a core prediction of our most successful theories of the quantum world. This vacuum energy is mathematically identical to the cosmological constant, that repulsive force Einstein introduced and then discarded, which we now recognize as the likely driver of dark energy and the accelerating expansion of the cosmos. Yet here lies one of the most baffling discrepancies in all of science. When physicists calculate the theoretical value of this vacuum energy based on quantum mechanics, the number they get is absurdly, impossibly large. It should be stronger than what we observe by a factor of 1 followed by 120 zeros. This is not just a minor error, it is the worst theoretical prediction in the entire history of physics. If the vacuum energy were even remotely that powerful, the repulsive force would have instantly blown the universe apart in its first moments, preventing even the simplest atom from ever forming. This colossal mismatch is known as the cosmological constant problem, a screaming contradiction between the world of the very small and the very large. It is a glaring sign that a crucial piece of our cosmic model is missing. Somehow, the frenetic energy of the quantum vacuum and the smooth, gentle push of dark energy must be connected, and understanding that link may be the final key to predicting the ultimate fate of everything. This gentle evaporation of black holes introduces a profound contradiction at the heart of physics. Stephen Hawking made the startling discovery that black holes are not the eternal prisons we once thought. Due to relentless quantum fluctuations at the very edge of the event horizon, they slowly leak radiation and lose mass over inconceivably long periods. This Hawking radiation means that a black hole can, in theory, completely evaporate, vanishing from the universe. And here we encounter the information paradox, a crisis that pits our two most successful theories against each other. Quantum mechanics holds as its most sacred rule that information is never truly lost. The specific quantum state of every particle that falls into a black hole, every detail of its existence, must in principle be preserved. It cannot be erased from reality. But if a black hole evaporates into a faint mist of random thermal radiation, where does that intricate information go? It seems to be irretrievably destroyed, violating a foundational principle of the quantum world. One compelling solution paints a breathtaking picture of the event horizon. The holographic principle suggests that all the information about everything that falls into a black hole is not lost inside, but is instead encoded on its two-dimensional surface, like a cosmic fingerprint smeared across the boundary of no return. The three-dimensional interior we imagine is merely a projection of this data, a hologram. As the black hole evaporates, this information could be slowly and chaotically released back into the universe, imprinted onto the Hawking radiation itself. Another idea posits that the information remains trapped in a tiny, stable remnant long after the evaporation seems complete. Resolving this paradox is not an academic exercise, it is the essential key to unlocking a unified theory of quantum gravity. It forces us to ask what reality truly is, and whether information itself is the most fundamental ingredient from which space, time, and matter are woven. That profound fine-tuning of our universe's constants presents a staggering possibility. What if our cosmos is not the whole of reality, but merely a single page in an infinite cosmic library? This is the Multiverse Hypothesis, a concept that stretches the very definition of existence. It suggests that what we observe as our universe, with its specific laws and constants, is just one region within a far vaster and more diverse meta-universe. In this grander picture, other pocket universes could exist alongside our own, each with its own unique physics. In one universe, gravity might be so strong that stars burn out in 1,000,000 years. In another, the nuclear forces could be too weak to form any atomic nuclei at all. These alternate realities would not be distant galaxies we could travel to, but entire separate domains of space-time, forever beyond our observational horizon. Where does this radical idea even come from? It emerges naturally from our most successful theories. The dominant model of the Big Bang, cosmic inflation, suggests that the rapid stretching of spacetime may not have been a one-time event. Instead, it could be eternal, with new pocket universes constantly budding off from the inflating background, each one crystallizing with a random set of physical laws. Similarly, the strange mathematics of quantum mechanics, with its myriad possible outcomes, can be interpreted as describing a reality where every possibility actually occurs, branching into its own separate world. While currently untestable and deeply philosophical, the multiverse offers a breathtakingly simple answer to the puzzle of fine-tuning. If there are an infinite number of universes, then it is no longer a miracle that one of them has the perfect conditions for stars, planets, and life. We simply happen to live in the one where the numbers added up. This idea does not diminish our universe, but rather expands the canvas of reality to an almost unimaginable scale, suggesting that the fundamental elements binding our cosmos together might be just one unique variation in an infinite ensemble of all possible realities. This line of reasoning leads us to a deeply personal question about our own place in the grand scheme. If the universe's fundamental settings appear so perfectly calibrated for our existence, does that imply we are the intended outcome or merely a fortunate accident? This is the core of the Anthropic Principle, a philosophical lens through which we view the cosmic fine-tuning. In its simplest, weak form, the principle makes a straightforward observation. We find ourselves in a universe capable of supporting life because we are here to observe it. It is a statement of selection bias, like a fish marveling at how perfectly water is suited to its gills. It does not explain why the water exists, only that the fish could not find itself anywhere else. The strong version of the Anthropic Principle, however, pushes into more profound territory. It suggests the universe's laws and constants might be the way they are because conscious life is a necessary eventual outcome. This perspective leans toward a biocentric universe, one where the presence of observers is a fundamental constraint on reality itself, as if the cosmos was always meant to wake up and look back at itself. This is not a testable scientific theory, but a powerful framework for interpreting the staggering unlikelihood of our existence. It forces us to confront two starkly different possibilities. On one hand, we could be the beneficiaries of an almost unimaginable cosmic lottery, the one in a trillion universe where all the dials happen to be set just right for complexity to arise. On the other hand, our very presence might be woven into the fabric of cosmic law, an inevitable result of a universe that is, in some deep way, oriented toward life. The Anthropic Principle does not give us the answer, but it sharpens the question, transforming the cold, hard numbers of physics into a deeply personal inquiry about why we are here at all. These frozen cracks in the fabric of reality could be the universe's most profound scars. As the newborn cosmos expanded and cooled, it underwent a series of dramatic phase transitions, much like steam condensing into water or water freezing into ice. And just as ice forms with cracks and fissures, the fabric of spacetime itself may not have solidified perfectly. Theorists propose that during these shifts, one-dimensional flaws could have been trapped within the very structure of reality, defects we call cosmic strings. These are not strings in any ordinary sense. Imagine a thread of pure energy, thinner than a proton, yet so incredibly dense that a single inch of it could weigh more than a mountain range. These filaments could stretch across the universe for light years, forming a ghostly web of unimaginable tension. Their existence would have left a permanent mark on the cosmos. A cosmic string would warp the spacetime around it so severely that it would act as a gravitational lens. If one were to pass between us and a distant galaxy, we would see a duplicate image of that galaxy, a perfect line of twin stars split by this invisible, razor-thin scar. Their immense gravitational influence could have served as the original scaffolding for the universe, the primordial seeds around which dark matter first pooled and galaxies began to form. The subtle gravitational tugs from a network of these strings, stretching and vibrating across the cosmos, might even have imprinted faint, telltale patterns in the cosmic microwave background, the oldest light in the universe. And when these cosmic flaws vibrate, or when two strings intersect and snap like overstretched rubber bands, they would send powerful ripples through spacetime itself, generating a unique low-frequency hum of gravitational waves that future observatories might one day hear. While still a theoretical specter, the search for cosmic strings is a hunt for a fossilized imprint from the universe's first moments, a direct relic of the violent processes that set the initial conditions for everything we see today. This delicate dance between order and chaos is written into the cosmic code. Even the most turbulent systems are not purely random. They are governed by simple, underlying rules that generate breathtaking complexity. A classic example is our planet's weather, a system so sensitive to its initial state that the flapping of a butterfly's wings could theoretically influence the formation of a distant storm weeks later. This is the famous butterfly effect, a hallmark of chaotic systems where tiny, unpredictable variations are amplified over time, making long-term forecasting impossible. Yet from this inherent unpredictability, patterns consistently emerge. A snowflake forms from the chaotic dance of water vapor in a cloud, each one a unique, intricate crystal built from a simple process of fractal branching. This is emergence, a fundamental property of our universe where complex, ordered structures and behaviors arise spontaneously from the interactions of many simpler components. The whole becomes something greater than the sum of its parts, exhibiting new properties that you could never predict by studying a single piece in isolation. Think of a single neuron in your brain. On its own, it is a simple cell that fires electrical signals, but when billions of them connect, something astonishing happens. Consciousness emerges, a rich tapestry of thought, memory, and sensation that cannot be found within any single neuron. This self-organization is echoed across the cosmos. The majestic spiral arms of a galaxy are not static structures, but dynamic patterns emerging from the gravitational interplay of billions of stars, a cosmic dance that could not be predicted by the laws of gravity alone. From the branching veins of a leaf to the intricate social networks of a beehive, complexity blossoms from simplicity. This principle suggests that the universe's richness and diversity are not pre-programmed, but are the natural, creative outcome of fundamental forces playing out within a framework that allows for both chance and law. The cosmos is not just built on gravity and light, but on the profound capacity for simple rules to generate infinite, beautiful complexity. Our cosmic web is not a permanent structure. The same dark energy accelerating the expansion of space today will ultimately dictate the final chapter of the universe, a future that grows progressively darker and more isolated. As the eons stretch on, the galaxies we now see will begin to vanish from the sky, not because they are moving away, but because the space between us is stretching faster than light can cross it. Their light will become so severely redshifted that it slips beyond any detectable wavelength, fading into nothingness. For any civilization born in the far future, the universe will appear as an empty, black void, with only the stars of their own galaxy, if any remain visible in an otherwise profound and eternal night. The grand cosmic connections we observe today will have been severed, leaving an island of matter adrift in an ever-growing emptiness. The ultimate fate of everything then hinges on the precise character of dark energy, a mystery we have yet to solve. One terrifying possibility is known as the Big Rip. If the repulsive force of dark energy intensifies over time, it could eventually overcome every binding force in nature. First, galaxy clusters would be torn apart, then individual galaxies. As the acceleration grows violent, stars would be ripped from their solar systems. In the final, horrific moments, planets and even atoms themselves would be shredded, their nuclei unable to withstand the overwhelming repulsion of space itself. The universe would end in a flash of disintegrated particles, forever isolated from one another. A far more likely, though no less bleak, scenario is the heat death. Here, dark energy continues its steady push, leading to a slow and cold demise. Stars will eventually burn through their fuel and die. Galaxies will drift apart into the endless expansion. Over trillions upon trillions of years, even black holes will evaporate via Hawking radiation. The universe will approach a state of maximum entropy, where energy is uniformly spread throughout an infinite volume. No more work can be done, no more stars can form, and no more complex processes can occur. It is the ultimate equilibrium, a cold, dark, and featureless silence that lasts forever. Yet our current understanding may be incomplete. New physics could reveal a cosmos that is cyclical, where a big crunch leads to a new big bang in an endless cycle of rebirth. Or perhaps dark energy will decay, allowing gravity to one day pull the universe back together. The long-term destiny of every atom, every force, and every memory of existence depends entirely on the outcome of this fundamental battle, a silent war waged between the binding embrace of gravity and the relentless, repulsive push of dark energy. Einstein's final dream remains one of science's most profound challenges. He envisioned a single, elegant equation that could describe the entire cosmos, from the immense whirl of galaxies to the frantic dance of quantum particles. This is the quest for a unified field theory, a theory of everything. It seeks to weave the four fundamental forces into one coherent tapestry. Imagine gravity, which shapes the universe on its grandest scales, finally reconciled with the quantum rules governing the other three forces: electromagnetism, the strong nuclear force, and the weak nuclear force. For decades, these two pillars of physics have existed in separate worlds. General relativity masterfully describes the cosmic stage, while quantum mechanics dictates the bizarre play of particles upon it. Yet when these theories meet, such as at the heart of a black hole, our mathematics breaks down into nonsense. The quest for unification is the search for a deeper language, one that can speak of both the stage and the players as aspects of a single, fundamental reality. One of the most ambitious candidates is string theory. It proposes a breathtaking shift in perspective. The fundamental constituents of the universe are not point-like particles, but unimaginably tiny, vibrating loops of energy, smaller than a proton by a factor of trillions. In this view, an electron is not a dot, but a string vibrating at one specific frequency. A quark is the same kind of string, just vibrating differently. The entire menagerie of particles in the universe becomes a symphony of harmonics played on these infinitesimal strings. The different vibrations manifest as different masses and forces, potentially unifying them all under one elegant principle. Another compelling path is loop quantum gravity. This approach takes spacetime itself and breaks it down. It suggests that space is not a smooth, continuous fabric, but is woven from a network of finite, tiny loops. Picture the fabric of reality as a chainmail vest, with each interlocking link representing a discrete quantum of space. This quantizes gravity, transforming it from a smooth curvature into a granular structure, finally allowing it to join the quantum world. A successful theory of everything would be the ultimate cosmic revelation. It would describe the universe at its most fundamental level, revealing a single, primordial element from which all forces and particles emerge. It could explain the very origin of the cosmos from nothing, illuminate the true nature of time, and finally answer the deep question of what truly binds everything together. This is not merely an academic exercise. It is the final frontier of our understanding, a search for the master key to the cosmos. Our journey from the force that anchors our feet to the ground to the light that illuminates our eyes reveals a cosmos more deeply interconnected than we ever could have imagined. We have seen gravity's grand hand sculpting galaxies, while the quantum realm's ghostly dancers built the very atoms of our being, with light threading through it all as an eternal messenger from the distant past. Yet for all we have uncovered, the profound mysteries of dark matter's invisible scaffold and dark energy's relentless push remind us that our map of reality is still unfinished, a coastline fading into the mists of the unknown. The physicist Richard Feynman once admitted with his characteristic honesty that nobody truly understands quantum mechanics. That is the beautiful, humbling truth of our cosmic exploration. It is not a final destination, but an endless frontier that forever challenges and surprises us. Let this glimpse into the universe's hidden binders ignite your own sense of wonder. The next time you stand beneath a starry sky, see it for what it truly is, a dynamic, evolving, and exquisitely bound together reality. We would love to hear which of these cosmic forces captures your imagination the most. Share your thoughts in the comments and subscribe to join us as we continue exploring the greatest mysteries of the cosmos.